Okay, so hi. We are going to do some related rates, and maybe this will help understand a little bit more about what they're doing in the process. So let's go ahead and make sure that we understand what related rates are. Now, a related rate is it's a rate. It's a rate of change of something. Usually we write d over dt. This means that this is something to do with the time. Remember, time is always a factor. So you have volume, you can have cost, we can have marginal cost, or we can have some sort of money, maybe like a liquid coming out, maybe just like an area. We can have a distance. They all have something involved, what we call time. And that's kind of what you have to think about when you're doing this. So let's go ahead and do a couple of derivatives. So if we take dx of, let's say, y to the third, well, technically you're differentiating y to the third with respect to x. Remember, this is the respect part that you need. When in respect to x, when you take the derivative of this, you have to make sure that there's a kind of an x in there. So here we go. So you're going to take the power, 3y squared, but remember, you're dealing with x, so it's going to be dy over dx. That part comes from there because you're differentiating with respect to x. So that's the derivative. But when we are doing related rates of that part, if we take the derivative of respect to t, let's say um, pi r squared, for example, the area of a circle, just one part of the area, well, that's going to be, remember, that's a pi is a constant. So that's just going to stay there. And that derivative is going to be 2 pi r, but remember, you're taking it with respect to time of r, so that's going to be dr over dt. So that's kind of what you need to develop when you're doing related rates with respect to the time. So let's do a couple word problems because I know that those are the hard ones. So let's do a simple one first. So let's kind of do an example here. All right. So let's say you have a ladder leaning against a wall. So here's kind of a ladder, and we can call that 10 feet long. So here's your ladder. Leans against a wall, and here's the ground. Okay. Well, think of the wall is 90 degrees toward the ladder. Now, what we want to do is think about our equation here. And maybe what happens is the ladder slips away. The ladder slips away, so it moves in this direction. And let's say that the ladder, the bottom of the ladder, goes away from the wall. So it moves away from the wall at a rate of maybe 1 foot, maybe a second. So that's the rate. Okay, at the same time, this piece comes down. So as this slides out, this piece comes down. You're still going to have a 10-foot ladder regardless. So let's kind of find some stuff about this. Maybe we want to find this. We want to say how fast, what's the rate, is the top of the ladder sliding down the wall. So you're seeing how fast is this going down the wall? When the ladder is 6 feet from the wall. From the wall. That's our question. So we want to find out how fast or what rate is the ladder slipping down when the thing is 6 feet from the ground. So let's make another picture, kind of see what's going on. So we kind of have this going. We have this. So this is 6. This is still 90. This is like your y. This is still going to be 10. And it's going down here. So I guess this is going to be a rate of dy over dt because this is the derivative or the rate of y. But remember that this is sliding out at 1. So we can say dx over dt is equal to 1 foot a second, but when x is 6 feet. So that's kind of the scenario, the idea of this. So what we are trying to do, that we want to try to find that. That's our goal. That's our goal. So let's work on that goal. So the first thing we got to do is kind of understand the picture. The next thing to do, let's write an equation. Remember, we need an equation of this because that's kind of the big mix of this. So if you look at the equation, it looks like we have a Pythagorean theorem. We have kind of like this a squared b squared equals c squared going on. So let's go ahead and rewrite this because if we have y here and maybe this is x, we can leave this as the radius, or c if you really wanted to, but c is going to be 10. So this is going to still be y, 6 and 10. So let's fill this in a little bit. Let's go ahead and call this 6 squared. This is your y, and this is 10 squared. Now let's go ahead and get y because we like to do that because that's what we're trying to find. If we do this, let's go ahead and get 36 y squared equals 100. So I guess we're trying to find the y value. That's what we're trying to do. Now, if you do this correctly and subtract this, I do believe that's the square root of, let's see, if you subtract that, that's going to be 8. Make sure you check the math on that. You move this over, subtract, take the square root. You have 8. Remember, we are making positive 8 because think about the scenario. We're going out. All right, so here we go. Well, now we have the other side. But remember, we want to find the dy dt. We have what this value is, but we need to find this, the rate. So the next thing we got to do is let's go ahead and take this old equation without the 6, and let's take the derivative of that. So let's kind of put that back where it says dy, and we can call it c, but really, remember, this is xy, and this is 10. So we can kind of just substitute that back in. Well, you know what that is. That's the ladder. And we kind of need to, remember, differentiate these both with respect to t. So if we do that, you get 2x dx dt. We get 2y dy over dt. And obviously this is going to be 0. Remember, we are doing this implicitly. Implicit. Okay? Well, if you look at the 2's, let's take a factor of 2 out. If we take a factor of 2 out, I'm hoping that you get to see this without me doing a whole lot of work, but that's okay. Take a 2 out. Well, really, that's going to go away because if you divide, you're still going to have this. If you divide, you still have all this. This is what we're working with now. Okay, let's go ahead and substitute what we have in, what we know, first of all. Well, we have an x. Remember, that's at 6 feet. So x is going to be your 6 feet. Remember, at time t. What is dx over dt? Well, isn't that dx over dt, isn't that the rate of the ladder slipping? Isn't that the rate of the ladder slipping? Because it's going 1 feet a second. If we look back at our picture, it's going to be 1 foot a second. It's slipping out when x is 6. That's why this equation right here has 6 and the rate it's slipping. Plus, well, we already figured out the y, which is 8. And by the way, we are trying to find this equals 0. And that's what we're trying to find. So do a little bit of math here, and we can move this over. So you're going to have 8 dy dt negative 6 multiply, move over. Now you're going to have dy dt, which is negative 6 over 8. What I would do is simplify this a little bit more because to make it a little bit easier to conceptualize. And I do believe that's 3 over 4. I think it's feet a second. That is the rate of the ladder falling down. So this is the rate of the, I think it was the top of the ladder, rate of the top of the ladder sliding. Right? That's what that is. So there you go. There's kind of an idea about, a ladder slipping down from a rate. So hopefully that worked out a little bit. So let's do another one that we kind of think that's a lot of work, and it is a lot of work, but it has the same kind of thing to it. Okay. So example. So for example, let's say we have this cylindrical cone. Looks like that. We have this, cylindrical cone, and we have some stuff working with it. Cylindrical cone. This radius is, let's say, 6 feet. So that's 6 feet. The height of the cone, the height of the whole thing, is 12 feet. I guess we should put feet, huh? Okay. Water enters the top at a rate of, let's say, 8 cubic feet per minute. So 8 cubic feet per minute. So that's the rate of the water seeping in. That's the rate of this going in here. Okay. Well, for example, we want to say how fast is the water level rising when the how fast is the water level rising when the water level is 4 feet deep? Now, how fast is the water level rising? So that means you kind of have something going on in here with another circle, and this is like the water. So this is the water rising, and remember, we're trying to focus on how fast is the water level rising. Water level rising, it has to do with height of that one. So this is kind of the liquid. So there you go. So we draw a picture, we kind of have an idea, but we want to clarify a couple things first. One is that what we're trying to find is the height to t. But we want to figure out when height is 4 feet long. This is what we're trying to find. We're trying to find the rate at 4 feet of how much this is rising. How much this is rising when it's 4 feet. And that's pretty much it. We have the circle, the big circle, the height, and maybe something down here. So let's go ahead and take this and make this work for us. Okay, so we know what we need to find. We have a picture. let's go ahead and look at a formula. So here's the formula. Remember, this is volume because water is seeping inside. So we want to kind of look at a volume. So the volume of a circular cone is almost like, so just a note, it's almost like something like this, like a cylinder, but it's been kind of cut in 1/3. So that's why it's 1/3 pi r squared h. Remember, this is the h. This is a circle, and it's kind of been cut to 1/3. And that's kind of what relates to a cylinder compared to a cone. I don't know if you knew that or not. If you didn't, that's okay. So this is like 1/3. So you can count on 1, 2, 3. Well, I want you to pick up this. There is two variables here. We want one. So we want one only. One variable only, because when we take the derivative with respect to time, this won't be in there. So let's do a similar triangles. Back in geometry here. So let's take our picture here and let's look at these two triangles. Now, if you look at these two right triangles, by the way, you're going to see something. So let's break these apart. So let's write them both. So I'm going to write these two triangles. And I'm just writing this picture right here. That's what my picture is. I'm just making it down there. I know that this is 6. I know that this is 12. If I cut this, not in half, doesn't have to be in half, but just you can kind of see it. Well, that's still an R. And by the way, that this is that height that it's filling up. So there's your similar triangles. Now, by the way, this has a 90 degrees here. Well, if we kind of split these up, which we could, and I'm going to show you how to do that. If I split these up, you're going to see something. This is 6, this is 10, then I make a smaller triangle. This is R, this is H. Do you see how this is could be a proportion because they're similar? So we're going to, as a proportion, here we go. We're going to go 6 is to 10. So we're going to go 6 as to 10 because this side is to this side, as this side is to that side. Do you see it? So if I start here and go to here, I need to go here to here. Is there other ways of doing this? Yes, but you have to be careful. You should get the same setup, by the way. But we're going to go this side is to this side equals this side to this side. Remember, it's a proportion, two fractions. Well, you have two fractions, proportions. Well, what do you know about proportions? They're equal, cross multiply. So if you cross, you're going to get 6H. If you cross, you get 10R. Right? Okay. What am I trying to do here? Well, I'll need to go back to here because this has an R and this is an H. What are we trying to find again? What are we trying to find? We are trying to find this right here. DH, not DR, DH. Well, think of this. What if we solve for R? So what if we solve for R? Let's do that. Let's solve for R. So if we solve for R, divide by 10. So that's going to be 6H over that equals R. Let's do a little bit of reducing here because, that's what we should be doing when we're doing this. And you know what? I think I messed up. Sorry. This is supposed to be 12. Sorry. Let's make that correction. So this is supposed to be 12. I misspoke. Sorry. This is supposed to be 12. So let's make that correction. So this is going to be 12 in R. Okay, just make sure that's correct. Well, let's reduce this. If you reduce this, don't you get H over 2 equals R? Is that true? That you get that information? Well, I want you to understand this. This is solved for R. If you go back to your equation, There's an r here. But r is h over 2. So if I take this and substitute it or replace for that r, I should have this whole equation in terms of h. I haven't taken the derivative yet. That's what I'm doing next. But I want to make sure that when I take the derivative, everything is in form of h. So let's take the let's go ahead and replace that. So you have v equals 1/3 pi, put a parenthesis, squared h. So this is going to be over 2. Do you see how the equation has all h's, but r was that? So we just use similar triangles to get this whole thing in h. Let's do a little simplifying before we take the derivative. So let's do a simplifying. We can kind of move this. That'd be pi over 3. Let's go ahead and use that exponent. So that's going to be x squared. That's going to be 4 times h. So let's do a little bit more here, a little bit more work with this because we want to make it a little bit cleaner. If you multiply straight across, you're going to get pi, 8 to the third, properties of exponents, x squared and h, make x to the third. And for 3 times 4 is 12. I'm going to do one last thing before we take the derivative to make our life a little bit easier. What I'm going to do is I'm going to separate our h's and our constant. Do you see why? Because this is a constant. It's the same thing here, but now when I take the derivative with respect to t, you're going to see why. So here we go. Take the derivative with respect to t, both sides. So what is this going to be? Well, that's just going to move over to be dv over dt equals, this is a constant. This stays where it is, times the 3 comes down, times h squared, what? dh dt, right? You're in form of h. So let's clean this up a little bit. So we have dv over dt. Let's clean this up. So the 3 over that. What is 3 over 12? Isn't that going to be 1/4? Or could I say pi over 4? Are you okay with that if I do that? It's just you're just doing this together. Just makes your life a little bit easier when you're doing this. And dt. Okay, there you go. Well, let's think about this. We need this. We need that. Do we have this? Do we have dv over dt? Well, where did that come from? That came from here. The thing is filling. The thing is filling with 8 cubic feet per minute. The thing is filling up. This is your volume. That's the rate. That's kind of like the liquid going inside the container is 8 feet. So right here, you're going to go 8 feet equals pi over 4. Oh, well, what is h again? Well, remember we talked about this. H was at 4. So we're going here. H was at 4. So we're going to put 4 in for where it says h. So let's make that a big 4. We're going to square it. And that's what we're trying to find. So let's do some basic simplification. This is going to be 4 times 4, which is 16. What is 16 over 4? Well, isn't that just going to be 4 pi dh over dt? Okay, divide. So you should have 8 over 4 pi equals dh over dt. And let's do a little bit of simplification. I think that's, what was that, 2 over pi? 2 over pi? Because this kind of goes away to 2. So, but if you don't want to do that, that's okay. But I do believe that the pi is in the denominator, by the way. So let's just kind of make this habit. Is that 2 pi? 2 over pi equals dh over dt. And I do believe that's your answer. Oh, be careful. They want the units. So we might have to play with the units a little bit. So this is what? Feet squared? Or, I'm sorry, cubic feet. So this is cubic feet per minute. There you go. You got to continue doing these a lot more because it gets to the point where it makes more sense as you're doing some math. But we needed to understand this point right here is the proportions and getting this in terms of one variable. Because when you take the derivative, it will give you what you want. Because if you didn't, you would have an R in here somewhere. If you didn't do that, you would have an R, which you would have to kind of substitute that and find that, and you would actually begin to do that same thing. All right, I'm hoping that this helped. It's only 2 examples, but there's plenty more, and that gets you started. All right.